My name is Eran Inbar and I'm the CEO of Prisma Photonics. And in the coming presentation, I will speak about oil and gas pipeline leakage detection, and to be more specific about robust qualification of fiber sensing for leak detection. And it will be based on our hyperscan technology. And let me start with the historical question, and maybe I would say a fictional historical question. Do you know whose statue it is? And just to give a hint, I would say that this is a famous Dutch boy. And the answer is that this is the Dutch boy that found out the leak in the Dutch dike and saved his city Haarlem just by stopping the leakage, by plugging his finger in the dike hole. And if we'll speak about the numbers behind it, so we're speaking about a small leak, 1 centimeter, a size of a boy finger, and this is correlated to more or less 100 liters per minute, a very small leakage over, if we will take the longest Dutch dike, it's like 35 kilometers. So one can say that probably the more difficult challenge is not to stop the leakage, but rather to detect such a small leakage over such a long dike. But I would guess that it's not part of the original story, because probably the author was not familiar with fiber sensing by then. But let's speak about detecting such small leakages over very long distances, and we will speak about the next generation of fiber sensing. So let's explain in just briefly what is fiber sensing. So fiber sensing is basically using standard fiber optic as sensor. So in our technology, we can use pre-existing standard telecom fiber as sensor, and it can be very long fiber. It can be tens of kilometers of fiber, and just by connecting the system, the optical interrogator to one side, we can turn this pre-existing fiber into sensor. And now it's done. We're transmitting light into the fiber, and we are collecting the small back reflected light that's returning back into the system. And now if we have an event close to the fiber, it can be, for example, a leakage from a pipeline a few meters from the fiber, or someone digging, as you can see in the illustration, close to the pipeline. This event would generate an acoustical or seismical signal that practically will affect the light. It will change the characteristic of the light, the amplitude, the phase, and then we can see this signature in the back reflected light. So we can eventually know three things. We can do a detection, know that there is an event. We can do localization. We can know the exact location of the event. And more important, we can do classification. We can know the type of the event. Is it a leakage, or is it someone digging, or is it someone walking? So this is in a very high level the concept of fiber sensing for leak detection. And let's speak about who we are, Prisma Photonics. So the company was founded in 2017, and our sole and exclusive focus is next generation fiber sensor for smart infrastructure. We are in revenue stage, and we already in commercial deployments of our technology. In this presentation, we will speak about oil and gas pipeline monitoring, but we're dealing with a lot of other aspects of smart infrastructure. Just a few examples. It can be electrical grid monitoring, subsea infrastructure, perimeter control, smart highways, railways monitoring, and even physical cybersecurity of optical network. Let's focus on pipeline monitoring, oil and gas pipeline monitoring. What are the use cases that this technology is enabled to detect and analyze? And first, and maybe the most important one, would be leak detection. But there are other very relevant use cases, like, for example, illegal tapping, that means theft from the pipeline. It can be risk to the infrastructure, like mechanical and manual digging in close vicinity to the pipeline. But also it could be third-party intrusions, like pedestrian activity, like vehicle movement, vandalism, and even drone activities, and also operational aspect. For example, inline picking devices in the pipeline itself. What is the difference between our technology, hyperscan fiber sensing, to the conventional, what it's called DAS, distributed acoustic sensing? So first of all, we are speaking about an ultra-sensitive detection technique. And one of the benefits of using such a sensitive detection technique is very long range. With a single optical interrogator, we can reach a distance of 100 kilometers of fiber or pipeline per single optical interrogator. But more important than the range itself is that this enhanced sensitivity enable us to be practically agnostic in the fiber type and the fiber type of installation. So almost any kind of pre-existing fiber in any kind of installation can be used without degradation in the performance of the system. The meaning is no need to install dedicated fiber, and on the other hand, no performance degradation if you're using fiber that it's not ideal for sensing. Additional and very important topics is the extreme data richness and quality, that means signal to noise ratio of this method, of the hyperscan method, and combining with machine learning classification capabilities, it can bring and solve what we say it's probably the holy grail of pipeline monitoring, and that's reducing the false alarm rate into a minimum, into practically zero. In conventional fiber sensing, you can take two approaches. One of them is to use pre-existing fiber. The other one is to use specialty fiber. If we're using pre-existing fiber, it's very cost effective, no need to install anything. It's a very fast ramp up of the installation of the system. The drawback is the reduced sensitivity. So we have very cost-effective solution, but with relatively high false alarm rate due to the reduced sensitivity. The other approach is to use specialty fiber. I would use my own fiber. I would install those fiber along the infrastructure. This is, of course, a much more complicated and cumbersome process, and the cost is correlated to it, but it will reduce the false alarm rate, performance versus cost. With hyperscan technology, you can enjoy the two worlds and basically achieve a very low false alarm rate, even though you're using pre-existing standard telecom fiber. Let's speak a little bit about leak detection and speak about leak detection records. And let's start with gas, and let's demonstrate ultra small gas leak detection. And this is practically the world record in gas leak detection. And what we're seeing here in this slide is the acoustical signature of the leak itself. So we can see the seismical map of the leak itself. And as can be seen, we can go down to a leakage as low as 200 standard liter per minute, and even go down to 100 standard liter per minute, just to give the percentage. It is correlated to a leakage which is 0.002 changes in the flow. So it's extremely low, low leakage. And just to give the correlation, or to give some kind of insight about it, what is 100 standard liter per minute? Think about a car tire that losing its air in 20 seconds. This is the level of this leakage. And if we're speaking about, for example, liquid leak detection, Here also we can reach an ultra small liquid leak detection, which is of course correlated to oil leak detection. And we're speaking about, and this is a very clear acoustical or seismical signature that correlated to 20 liter per minute, which is basically correlated into 0.02% of a change in the flow. So once again, very low leakage, just to give the indication what is 20 liter per minute. So it's correlated to think about a water canister that it's being empty in 1 minute. This is 20 liter per minute, just as a reference. And another very important issue regarding to both liquid leak detection and also gas leak detection, that those detection algorithms are not relying on momentary and transient effect. So we're not using effect like negative pressure pulse, which are transient effect and happen for a brief in a one-time event. And the risk of using transient or momentary event, that if you did not detect them, that's it, it's a one-time event, and it will affect the probability of detection. So our technology or our concept is using the continuous flow of the event. So even if you didn't detect them in the first second or the second second, you still have the event and you have the ability to detect it later on, and therefore you can achieve a very high probability of detection. Last thing to speak about is a third-party intrusion, and here classification is a key. Because when we're looking to third-party intrusion, for example, we would like to detect mechanical digging close to the pipeline because it's very high risk, but we would like to filter them and not giving an alert about, for example, someone walking close by or a vehicle driving in a nearby to the pipeline, because otherwise we can get a huge amount of false or nuisance alarms. So classification is the key in achieving very high probability of detection combined with practically zero false alarm rate. And here is an example. So we have here, as you can see, a digger. And in the left slide, you see the digger when the engine is off. So no indication about it. You can see that alert level is low. And on the right image, we can see what's happened when the digger just turned the engine on. Not yet digging, just turning the engine on. And here is the seismic trace or the seismic signature of the engine, and we know that the engine of the digger is on, and we increasing the probability of detection from low to guard, because we know that there is something to put an eye on. And what's happening when the digger starts to dig? What's happened when there is the first scrape on the ground? We not just know right now that there is an engine and there is a first scrape on the ground, and we can increase the probability of detection to high and put the alert on yellow. And right now we are waiting for the second scrape or the second dig, and once having it, in this case 9 seconds later, we can have a very high probability of detection. We can increase the probability into severe and raise the alarm. And this is done with a very high probability of detection, but this process basically eliminates almost all of the false alarm rate correlated into detection diggers walking close to the pipeline. So, to summarize, we present the next generation of fiber sensing using any kind of pre-existing optical fiber. We are speaking about ultra-sensitive detection technique with practically zero false alarm rate, and the combination of advanced machine learning classification of events allow us to maintain very high probability of detection with practically zero false alarm rate. We're speaking about deployment in practically hours because we're using pre-existing fiber, no need to install anything along the infrastructure, and covering hundreds of kilometers of pipeline using one system per 100 kilometers. Thank you very much.